Hi everybody. The topic for today is section 17.2, which is called line integrals. This is going to take a little bit of time to connect to 17.1 where we saw vector fields, but it's coming. But first we're going to look at a simplified version of a line integral where there's no vector field involved. So kind of a preliminary thing. What are called scalar line integrals. So what is a scalar line integral? It's got essentially two components. There's a curve, which in the whole line integral world, I think we always use sort of a cursive C for a curve. In other words, this is a space curve. One of the things we studied like 3 chapters back. And so it could be a space curve in R2 or in R3, but I'm gonna do it in R2 for us to visualize that. And then the second ingredient is a function, a scalar function, that goes from, whose domain is the same as the domain, the range of the space curve, the dimensionality of the space curve. So typical then for this would be C is a curve in 2D. Or in other words, a curve in the xy plane. And then the function is going to be a function of 2 variables, x and y. Well, maybe instead of trying to describe that in words, let me just write it. F equals some function of x and y. So let me illustrate that sort of setup. To graph a function that has 2 variables as its input, we need to be in R3. But this space curve C is in R2. So let's take a look at how that setup is going to look. We'll be in R3 in a sense, but there's a plane down here below that is R2. That is, this is the XY plane seen in perspective. And the point is C, this curve we're working on, lives down here. That's where C is, something lying flat in the plane. I hope that looks like it's lying flat in the plane. Driving around like that on the plane. Then we've got our function, which is, z equals f of xy is its graph. That should be visualized as a sort of, I like to call them magic carpet drawings. There's a surface up here. And you could even think of it as having rules along it to indicate, I don't know, sort of show the grid work of the XY plane up there on that surface. Well, what we're going to do is integrate along this curve the height up to the surface. So I always talk about it as being curvy walls. Let me just sort of draw a straight line. Not with that marker. Oops. Draw a straight line. The markers are about to fall on the floor. Draw a straight line up to the surface. All along this curve, do that. Well, that wasn't a very straight line, was it? And there'll be a sort of projection up. So I'm drawing up from the curve C onto the surface. What we've just created here is a thing that could be straightened out and made flat, and you could figure out how much area it has. So that's actually sort of conceptually what we're going to do. We're going to think about the area along this curve, so between some point here on the curve and here on the curve, of this wall that is got a curved path, but it's also got a curved height. That is, both things are variable. The curve may go like this in the xy plane, but also the peak of it doesn't stay at one height. It changes according to what the function z equals f of xy tells us. So could you work out the surface area of a curved wall with a curved top? I feel like that's sort of a good way to say it. So let me just write that down. First, surface area of a curvy wall, can't spell, curvy wall with a variable top, maybe? Or maybe it's a better way to say it is a variable height. So unfortunately, the way this thing got drawn, it looks like the heights are staying relatively constant on there. I think my surface didn't have a whole lot of up and down in that region. But generally speaking, the surface could go way high over here, way low over here, and you'd get the height of that wall changing, as well as it's a weird wall that has a wave to it. Well, how do you do a thing like that? You should probably think about Riemann sums a little bit. You see the curve here, you actually have to have some sort of mathematical description for it, right? So typically you have a position vector, r, which is a function of time. And we're going to need time to go from wherever it is when we are at this end to wherever it is when we get to that end. That is r of t, where t is in between some limits. Right, so what I'm saying is this beginning point of the curve would be r at A, and this ending point of the curve, that would be r at B. So if you think about this in terms of Riemann sums, there's going to be little strips that have heights determined by, by the surface, right? And their widths. And the widths are going to be interesting because the space curve does not necessarily travel, at the same rate down this curve. It might be going very slow down here and very quickly out there. In which case, 1 second at a time might be 1 foot here, but 1 second at a time might be 3 feet over here. How do we account for that? Basically, we just scale up the width of the elements of the Riemann sum by the speed of the curve. So that's something that we need to take a second to just think about. You know the Leibniz notation for the... I just had to stop and rethink how I was going to explain that. The thing we want to do is actually go from this description r of t, where you're moving along the curve in some way prescribed by time, to a different description of the curve, where you're moving along at the same speed all the time. That is, following it at constant speed. And the good way to do that is to parameterize the curve by arc length. So we want to go from r of t to r of s. So that where you are depends on how far you've traveled as you're moving along the curve. And what's really going on there is that there's the arc length function. That there's this function, s is a function of time. It tells you how far you've gone. Now, what is the velocity, or what is the speed as you're moving along that curve? Right, so let me give myself a little more space for that. The arc length function is basically an integral from where you started to a particular t somewhere down the line. So think about, I know you want to think of t as the variable, but imagine we've moved all the way up to some particular time t. Okay? The arc length along that curve is just the integral of its speed as you move along the curve between a and t. So this is the arc length, integral from a to t We need the speed of the thing as we go along, and I'm using t as the variable, well, as the particular position we're thinking about, the particular time rather we're thinking about here. I need a different variable to use as the what was formerly t. So I'm going to use u. That's what they do in the book too. I'm going to take r's derivative, think of it as a function of u, take the length of that and integrate it with respect to u. That gets you s of t. But honestly, we need s of t mostly as a a conceptual tool, a theoretical tool, because we literally do want to keep the parameterization we started with, integrating with respect to time. We just need to take into account that when we integrate with respect to time, our change in position is variable. So let's call the arc length function s of t. What do you get if you take the derivative of that? That's your speed. Well, yeah, that's your speed, because this is how is the position along the curve changing with respect to time. Let me just write this in the Leibniz form though. Write it as ds dt. There's another way we know to say what's your speed, and it's this. Take the derivative of r and, absolute value of it. So this is also the speed. The derivative of the vector function, r of t. Should put a vector hat on it, shouldn't I? Oh, I'm just looking back, I see I left a vector hat off of this one. Anyway, yeah, that is s prime, which is ds dt. Which means I can take this relationship and solve it for either dt or ds. I'm gonna solve it for ds because that's the one we're actually interested in. ds is length of this velocity vector times dt. Which means I can do an integral to find the area of this curvy wall with respect to s without even knowing what s is, because I just used the derivative of the position vector and dt. That is, conceptually I'm doing it with respect to arc length, but in truth I'm doing it with respect to time with this correction factor in there to make it all right. That's all fine, but I think we better do an actual example of that in order to sort of get a real grip on what's happening. So the function f of xy I'm going to use will be 1 plus x times y. And the curve C is going to be the unit circle. That's a nice one to start with. But just the part in the first quadrant. Well, that I can parameterize real nicely. So our position vector, r of t, is going to be cos t sine t. And to make this happen in the quadrant 1, I'm going to limit t to go from 0 to pi over 2. That's weird. Pi over 2. Okay. Now this particular surface has a saddle shape, right? It rises as you go out into quadrant 1 or into quadrant 3. It descends as you move into the quadrants 2 or 4. That is, it goes lower. And this, in the xy plane, this just looks like a quarter of a circle. So let's try to sketch what we're dealing with here. There's the xy plane. Here's a quarter of a circle in the xy plane. And then we've got this surface up here that's rising there and falling that way. It's a little hard to sketch, but you know, it's like a Pringle check. We've seen that before. So my wall is going to start out relatively low and rise, because this is the line y equals x, to a high spot right there, and then it's going to descend again to a much lower spot. So it's going to be curving around a quarter of a circle, but then rising up and then descending back down. It's a fairly freaky looking piece of wall there. How much area does it have? Well, what we need to do is integrate with respect to arc length, the height. So we basically need to integrate z ds. And that would be, well, from whatever the s parameter or whatever, but we won't. What we're going to do instead is convert everything into the things we can say in terms of this position vector. All right, so what's r prime? Kind of want to get rid of that dv integral with respect of z with respect to s, because we really aren't going to use it. The derivative of our position, our velocity vector, is negative sine t cos t. And that's a particularly nice parameterization because the length of this r prime of t is 1. You probably recall us doing a bunch of things where we took advantage of the Pythagorean theorem. When you figure out the length of this vector, you end up with sine squared plus cos squared, so you get to 1. That means ds and dt are the same thing. ds is equal to 1 times dt. So we're already integrating with respect to arc length in this simple example. What does our function become if we're restricting ourselves to lie above this point, this moving point in the xy plane? The integrand, the z, let's just say the height, it's going to be 1 plus cos t sine t. So here's what we need to do to get the area of that curvy section of wall. It's going to be the integral from 0 to pi over 2. Those are the endpoints determined by here and here, right? Where we're at this location right here when t is equal to 0. And we're at this location when t is equal to pi over 2. Starting out on the x-axis, moving around onto the y-axis. Never labeled the axes, did I? So that's the span over which we integrate. The thing we have to integrate is this height times ds, but that's the same as dt. So 1 plus cos t sine t dt. I can't think how to integrate that. Oh, maybe you can. Yeah, you can split it up into 2 integrals and then use a u substitution, because yeah, if u is sine t, then cos t would be du, or cos t dt. Yeah, you can do that, but that's actually not the point, whether we get something we can actually integrate, because if you can't, it's fine. Turn it over to a computer and get a numerical integral. The real issue was just being able to set up an integral in terms of our t parameter for the area of that curvy thing. All right, so now we should be in a position to hook this up, the stuff we've just done on line integrals of a plain old function, up with the stuff we did in the previous section about vector fields. The basic idea is we're going to need to get the scalar to be something that's dependent on the vector field. So integrating a vector field along a curve. You can actually do this in 2 different ways. Well, at least 2 different ways. What I would like you to think about is, as you're moving along a curve, there's, at some point on the curve, say here, there's the little Frenet frame that we have used before. So there's a vector that points in the direction of the curve, that's unit length, vector t, and then there's a vector that points orthogonal to the curve, and that's vector n. We don't need b, so just t and n is sufficient. At least we don't need it for now. Anyway, so you've got t and n, and you imagine this point in motion along the curve, and t and n are moving along with it. And then there's the vector field, which I'll just sketch in some representative vectors here. I don't know, just got to get enough of them, but it looks like a wind map is what we really want to have happen there. Okay, and there's two different, because we have two different vectors on the curve and this vector field. There's two different kinds of scalars we can produce that we could integrate. One is to dot the tangent vector with the vector field, and one is to dot the normal vector with the vector field. So that is, we can get integrals along the curve of t dot, what we call in that vector field, let's call it v, with respect to s, or we can do an integral along the curve of n dot v, again with respect to arc length. So those are the two kinds of line integrals that you can get. They're physically meaningful. T dot v gives you a sense of how much the wind is blowing in the direction of motion. So like that's what people who command sailboats do. The wind, if the wind's pointing in the direction of motion, it's all great, and you move down the curve. If the wind is pointing against the direction of motion, then that's not good, and you get stuck. So there's actually a term in the old days in sailing. They would talk about the wind gauge, meaning to what extent was the wind favorable to one sailing vessel over another. I'm thinking about warfare at this point. So when sailing ships, the old school things with the giant, square rigged sails and everything, they would have to fight each other. Coming into a scene of battle with the advantage of being upwind was really good. Anyway, the thing that you get when you dot the tangent vector with all the vectors as you move along this curve, and we should really think about this as being like almost a Riemann sum kind of deal. There's a tangent vector here, and there's a wind vector or a vector field vector at that same spot, and you dot them and you get a number. And then there's a tangent vector there and a wind vector there, and you dot them and you get a number. And so you just keep working your way down the curve with tangent vectors and evaluating the vector field at that point, getting a number, and then you just add up all those numbers. That's the Riemann sums way to think of it. Of course, the calculus is to take that to the limit, and you're just doing this. T dot v ds integrated. In a lot of physics applications, this integral is called a work integral because if you think of these vectors as forces, like in a magnetic field, it's a force field, and you're moving along in the direction of motion. It could be electrostatic field, and these are a charged particle in motion along this line. The result of that path integral or that line integral is actually how much work is done on the moving object by the vector field. It can be vice versa. It can be the amount of energy that the field gives up to the object. You can think of it as either work or energy, because honestly they're the same thing. The other kind is known as a flux integral. Am I doing that right? Flux and flow. Yeah, these kinds are called flow. That kind is called flux. But we're going to get to that terminology later, so don't sweat it. And actually, I wanted you to know that there were two different ones, but we're going to concentrate at first just on this kind. Because in physics in particular, that's that's one of the most important types of integrals because it calculates energy or work. All right, so I just noticed that in the book they don't call the vector field V, they call it F. So let's say F is a vector field, capital F is a vector field. And R of t describes a curve. Oops. I guess I'll call the curve C as usual. That would be with t within, traditionally we use limits a and b for t. So the sort of integral we're after is integrating the tangent vector for that curve dotted with f. So f dot t, so those are vectors with respect to arc length. This integral done over the curve. Well, let's take apart some of these things. T is actually r prime divided by r prime's length, or to turn r prime into a unit vector. So you could re-express that as the integral over the curve of whatever f is, dotted with r prime of t divided by the length of r prime of t, ds. Well, a little bit ago I mentioned that ds and dt were related to each other, and how they're related is by the speed. So this is the same as integrating over the curve f, I'm just copying this stuff so far, r prime of t divided by the length of r prime of t and then ds becomes the length of r prime of t times dt. That's a dot product. So these two are a scalar, and then that's scalar multiplication afterward. All right, so, well, it's clear these two cancel, right? So our arc length can be just written as f dot r prime dt. Now I've left f alone. Ordinarily f is going to be a vector field that's a function of x and y, and we're going to actually, in there, you're going to need to compose f with the position vector. So that in the end you find, for a particular time, what the vector field is. All right, so we've got the integral for integrating our vector field along our space curve down to this sort of thing. You can now put actual limits in because you're integrating with respect to t, and those are the t limits. But we can take this a good bit farther if we go to the trouble of specifying sort of what the insides of f and r are. So r is easy, I think. You want to think of the vector r as being a vector that consists of a function of t that gives you the x-coordinate, a function of t that gives you the y-coordinate, and a function of t that gives you the z-coordinate, and you might as well call those functions x, y, and z respectively. For f, we'll just choose names, and I'm going to stick with what they did in the book. But f is a vector field, right? So it's really a function of position. So what I'm actually going to write is not f, but f evaluated at r, which is itself a function of time. So that makes, in the end, that makes f a function of time. I think that's understandable, right? So do I need to actually put that in there? What we're doing is getting the value of the vector field at a position that corresponds to a specified time. And so we'll just think of this as being f as a function of t. And that's going to be 3 components, little f, little g, and little t. H, I'm sorry. I was writing a T when I made my mouth say T, even though I was supposed to say H, F, G, and H. Oh, you know, I've sort of implicitly moved to 3 dimensions. If this was not 3-dimensional, we would just end the vectors here, right? But that's okay. We can do it for 3D too. It's not much of a difference. Then, having specified these names for things, I don't want you to think this follows from anything that went before. This is just us choosing names for the coordinates of r and for f. But notice what this now looks like. We're integrating from a to b. F is the vector f of t, g of t, h of t. And r prime is going to be x prime, y prime, z prime. And hopefully I have just enough room in here to get a dt on the end. Well, of course, you can do the dot product, and that makes it look like, let's see, f of t times x prime of t plus g of t times, that'll be y prime of t. And finally, h of t times g prime of t. All times dt. So we should probably put parens around all that stuff. Well, I don't see him doing it, but you know, this is a sum, right? We're integrating a sum of things. You know how integrals distribute over sums? So you could think of this as sort of 3 separate integrals, or at least it looks like you could. At least we could sort of think about distributing the dt's across through this stuff. And I want you to think about what is the meaning of x prime of t, or y prime of t, or z prime of t. I guess it's in this. It's in the Leibniz notation where you say dx by dt is equal to x prime. So if I've got an x prime and I've got a dt over there, the nice form of this is multiplying through by dt. And that sort of thinking will let you replace x prime and dt with dx, which is well, it's just notation, but it is really a more compact way of writing the integrator. So let's see. I guess I need to work up above. I want to save this line so that we can copy it in properly. But you see, once we replace x prime times dt with dx, the integrand becomes a lot easier, or what? I don't know. The form of it is certainly simpler. We have f of t dx plus g of t dy plus h of t dz. Actually, often people just don't even write the of t's on these things. They just say f dx, g dy, h dt, dz. I notice that's how they've done it in the book. Well, okay. That, once again, looks like a dot product, doesn't it? That looks like the dot product of the vector field, let's drop the arguments to the functions and just say FGH, dotted with a vector that has these differentials in it, dx, dy, dz. And people tend to want to have a name for a thing like that. And it's, well, it's got a name that makes perfect sense if you look at it from the right perspective. That vector full of differentials is called dr, where r is a vector. So this piece here, this whole thing, call it dr, vector r. Why do you say that? Well, if you had r given, what's r prime? It's the derivative of x of t, y of t, z of t. Oops. Sorry. It's the derivative of that vector. But it's also, in the Leibniz notation, it's dr dt. Okay. And if I prime that, what I get is that dr dt is equal to the vector that has x prime, y prime, and z prime in it. I think I'm going to, should I skip the arguments? Sure, let's skip the arguments. X prime, y prime, z prime. So if you wanted to solve for dr, you would just multiply both sides of this by dt. If you multiply the dt in and replace x prime dt with dx, you've got the thing we're after. So dr, it really does make sense to call the vector containing these differentials for x, y, and z, to call it dr. So that is a sort of final way to write the integrals we've been talking about. I've shown you lots of different forms for it, but the sort of cleanest form is this. You're integrating f dr. Maybe I should say f dot dr, since dr is a vector. All right, so there's a chart on page 1103 in the book that kind of runs through all of these different forms I've shown for the path integral, or the line integral there. I think we would be remiss without actually doing a real example of this. And when I did this in class, I used a fairly simple example. I think Let's first of all, I'm going to do a 2D example, because 3D is only, I mean, you know, doing 2D or 3D is almost the same thing. It's just whether you have like 3 vectors or like 2 vectors. I've forgotten the example I did in class, but I do remember the curve. I made the curve go the unit circle all the way around. So it's your r of t would be cos t and sine t in its components. And that would be for t between 0 and 2 pi. The vector field I chose when we did it in class, the arc length integral came out 0, and I think I wanted to make sure that people didn't think it always comes out 0, because this is a closed path. We went all around a whole circle. So let me give you a different vector field, and you'll see for this vector field it won't come out 0. The field I'm going to use, F, is the negative of y comma x. Okay, so this is the example I want to run. We'll go all the way around the unit circle, letting t run from 0 to 2 pi, and we'll use F as this integral, this vector field. Okay, that's actually really easy to re-express right now in terms of time, because the position vector is sitting right above us. So when this is in the x coordinate, it has negative y, that's y. Okay, this is x, and that is y, if you're on the curve. So this guy becomes, as a function of time, it becomes the negative of sine t and the cosine of t in the other coordinate, in the y coordinate. So if we integrate over this curve f dr, I'm going to actually bring it back to the original form we had. You're going to have f dotted with the tangent vector, which happens to be just r prime. So the f, I already told you what that was in terms of t. The tangent vector, I think we can do that in our heads. We'll just differentiate cos t and sine t. Derivative of cos t is minus sine t. Derivative of sine t is cos t. And as before, this is the unit circle, which parameterized the way we have done with t being in radian measure, basically. That means you're moving at unit speed around that unit circle. So arc length and time are equivalent. That is, this is fine if you just write dt rather than ds. Or if you like, you could write a 1 here because the speed is 1. All right. What are the limits on this? I had said previously that t goes from 0 to 2 pi. So we've turned it from a sort of an abstract integral to really a concrete one. And when you actually do this dot product, you see how you get 2 minus signs cancel. It ends up being sine squared plus cos squared. So the integrand is 1. And so when you integrate, you get t, or the antiderivative is t, and then evaluating, you're just going to get 2 pi. So we didn't need to get 0. The example done in class, it came out 0, but it might have made people think that it always is going to be 0 if you kind of end up back where you started, like this integral does. We start at 0, we end at 2 pi. Well, those are actually the same point in the xy plane. So we have a closed loop. This is an integral where the thing you get actually is non-zero. And in fact, I should probably sketch this for you a little bit. The unit circle certainly is easy enough. That's the unit circle going from 0 to 2 pi, returning to the same position, but at a different time. What does the vector field look like? Well, let's see. The easy vectors to figure out are what does it look like when we're at the on the axes, right here, here, and here. So this is when, well, I guess I could either do the t version of things or the x and y version of things. Let's do the x and y. This is x is 0 and y is 1, right? So the vector you get is minus 1, 0, which looks like this. At this point, x is minus 1 and y is 0. So the vector we get is 0 minus 1. That's one that goes downward in length 1. And let's see, here we're at x is 0, y is minus 1. That's going to give us a plus 1 in the x coordinate and a 0 in the y coordinate. That looks like this. And maybe you get that the last one's going to look like that. In fact, this vector field is what's called a circulation. It's like a pinwheel. Work out what it looks like all around. The vectors are spinning around in a circle. So if you think about this in terms of tangent vectors and these guys, the tangent vectors and the vector field vectors are all pointing in the same direction. In fact, they're both unit vectors. So the dot product you get is 1, and that's what we got, 1. And then you integrate 1 all the way around the circle, of course, you're going to get 2 pi. All right, so that's basically a redo of what we did in class. I did a slightly different example at the very end, and I did just a little more on the alternate notations for the path integral, but that should be good.